Hi. In this video, we'll build a simple sales forecast solution from scratch using InVision and Flow. We'll forecast the number of units sold by department and product for each period. We'll add a spreadsheet for data input, create a chart to show the sales forecast by month and shipping costs, and enable users to comment on their forecasts. When users save their changes, the solution will recalculate the forecasted monthly sales and amounts and shipping costs based on a price list and seasonal adjustments, then refresh the report automatically. Let's start by creating a new solution in the InVision Designer and set up the initial solution structure. I'll quickly add the department and product dimensions to the solution, since those are the dimensions we will forecast for, and then define the key fields for each of them, which will be department ID and product ID respectively. I'll then go ahead and add the data store to the solution where we'll store the forecast input from users. A data store is materialized as a database table in SQL Server, but it also lets us define a lot of additional behavior and business logic, such as relationships to dimensions and time intelligence, plus much more that we will not cover in this video. I'll start by adding the product ID and department ID columns, since that's the dimensionality we'll be forecasting for. I'll then add 12 columns representing the periods we'll forecast for. In InVision, we call these timeframe columns. Timeframe columns each represents a period of time, for example a month, a quarter, a year, or any arbitrary period of time such as 7 months. When you create a data store, the default resolution is month, and the timeframe starts at the beginning of the current year. You can change all of this in the timeframe settings of the data store, and even choose whether to use natural or fiscal calendars. In this demo, we'll just use the default settings and add 12 timeframe columns to represent an annual forecast starting in January. Finally, I'll just add a totals column to keep the sum of each row. Next, I want to configure my data model so there's a relationship between my data store and my dimensions. This makes it easy to later apply filters, access control, build the UI for input, and create reports. To do this, I simply find the department and product dimensions and double-click to add them to the source mapping list. In the Columns Binding tab, I can now simply click Auto Bind to define the relationship between each dimension and the corresponding column in the data store. This works because the column names in the data store match the names of the key columns in the dimensions. If they didn't match, I would need to manually map each dimension to the appropriate column in the data store. The next thing I'm going to do is add a worksheet to the data store. The worksheet lets users edit data in the data store in a tabular format, similar to a spreadsheet. You can add multiple worksheets to a data store, each with its own set of columns, rows, and business logic, but in this demo, we only need one. The first thing I do is pick the columns from the data store I want to use in the worksheet, which in this case is all of them. Next, I want to hide the department column because it will only be used for filtering and not for editing, so there's no need for it to be visible in the grid. What I want, though, is for users to be able to select products from a list in the grid once they've chosen a department to forecast for. To do that, I'll specify that my products column has a drop-down list, and that it gets its values from the product's dimension. In this demo, I only want users to be able to forecast on the leaf-level products, so using a drop-down list is the most straightforward approach. If I wanted users to be able to select from multiple levels of the product's dimension, I could do that as well, but that's a topic for another video. With the department and product columns fixed, I now want to do something with the forecasting period columns. Having them display P01 to P12 is not very user-friendly, so we'd rather want them to show the month and year that they actually represent. To do that, I can use the caption expression property and specify that I want to display the year and month that this column represents. Remember what I said earlier about timeframe columns and time intelligence in the data store? Because P01 to P12 are timeframe columns, I can use time intelligence functions like DateStart to format column captions using format strings. Let's just quickly adjust the width of the column as well, before we create the workbook that displays the worksheet to the user. Once we've seen the initial UI, we'll go back and fix the remaining 11 period columns. I'm now going to create the workbook where we'll do our sales forecast input and later view reports and manage parameters for calculations. I'll just give it a suitable name and add a page. Then, I'll find the worksheet in the toolbox and drag it onto the page and size it to fill half the height and full width of the page. I want to add 2 buttons to the page, so I'll adjust the top grid track to accommodate them. I usually prefer 50 pixels height and 120 pixels width for grid cells containing buttons. Note that buttons will stretch horizontally, but not vertically, so setting the height to more than 50 just increases the space around the buttons. I want my first button to save the data in the worksheet, and the second button lets the user refresh the worksheet manually if they want to. I'll give each button a name, display text, and an icon. Then, I'll define what happens when the buttons are clicked. Later in the video, we'll add more functionality to these buttons. To define what happens when a button is clicked, simply add a handler and then drag and drop the action of the target component into the actions list, like I'm doing here with the save and load actions of the worksheet component. There are a lot of additional options available for configuring what happens when an action runs, but that topic is too big for this video. With the page selected, I add an event handler for the loaded event, so that the worksheet is loaded the first time the page is displayed. With the basic setup complete, we can go ahead and view how the workbook looks by pressing the preview button. This will open the workbook in a new browser tab, and as you can see, the buttons and worksheet renders as expected. Remember that we only configured the January column to display month and year, so let's go back and fix the other columns as well. Switching back to the browser, we can see that all the other columns displays correctly as well. Layout changes to worksheets happen automatically when the dev equals true flag is set in the URL. The next thing I want to do is add the department filter to the workbook so that users can select which department they want to forecast for. Back in the Solution Explorer, I add a new filter component and select the department dimension as the filter source. Then, I need to go back to the worksheet and associate the department filter with the worksheet. Because the column name in the worksheet and the column name in the dimension match, the association is made automatically. Back in the Workbook Designer, I can now drag and drop the department filter onto the left sidebar of the workbook. Putting it in the sidebar makes the filter visible across all pages, and it also enables sliding the filter in and out of view as needed. Before switching back to the browser to see how it looks like, let's associate the department filter component with the worksheet, and then configure that the worksheet should reload when users change the selected department. We do that by handling the selection changed event of the filter and run the load data action of the worksheet. Because of the association, the worksheet will automatically update its data based on the selected filter values. Back in the workbook, we now have a filter on the left side, so that's looking good. But there's no data, so that's what we'll work on next. What I'll do now is create a workbook and add a dimension editor component to it. The dimension editor allows users to manage dimension data in hierarchical structures, using drag and drop to rearrange items, taking backups, and much more. I'll then use the dimension editor to fill the department and product dimensions with some sample data that we'll use for the rest of the demo. With data now available in the filter source, I need to tell the department filter to load its data. For this demo, I'll simply load it when the workbook loads initially, but filters can be loaded on demand at any time as well. As you can see, when I now select a department in the filter, the worksheet on the right reloads automatically. What I want to do next is add a formula to the worksheet so that the totals column is calculated whenever the user edits the period columns. To do that, I simply add a formula that sums the values in the period columns for each row. The syntax is similar to how you would write it in Excel, but has some differences, so I recommend checking the documentation for details. Let's try everything out by selecting a department, adding a row, input the number of units we expect to sell for a specific product, and observe that the totals column is updated. If we now click the Save button, the data is also saved to the database. The next part of the demo will be slightly more technical. We're now going to build the calculation logic that takes the user input in quantity and calculates the forecast in amounts based on a price list and seasonal price adjustments. We'll also throw in calculations for shipping cost. Note that I'm just making up the business logic here for demonstration purposes to show the capabilities of the platform. A proper sales forecast will of course be more complex and involve many more factors and other calculations. The first thing I'm going to do is create a view that unpivots my period columns into rows, so that I get the data on a transactional format with the dimensionality intact, but one row per period column converted to an amount and transaction date column. We do this because it makes the calculation logic fully dynamic, so we can actually add more or remove periods in the future without having to change the calculation logic. Next, I'll add a data store to save the transactions from the sales forecast calculations. Later on, we'll use this data to build reports. I want my data store to contain the same dimensionality as the input data, and I also want it to contain a column that identifies what an amount is for. In typical finance applications, this is usually an account, but I'll call it Calc ID in this demo. It serves the same purpose. I'll next add my price list table so that we can calculate amounts based on the quantities provided by the user. We'll keep it simple by just including the product and the price, assuming the price will be the same throughout the year. To handle seasonal price adjustments, I'll add a separate distribution key table shortly. You could also include a date column here if you wanted more granularity in your pricing. To expose the table as a resource that can be used as a dimensional lookup table in Flow, I need to change the function setting from default to lookup table. I also want to go into the Listing tab and specify that I want the table to be displayed in a Table Explorer component. This is a feature that allows users to browse and edit different tables in a single interface, making it easy to manage many datasets. Let's add a table for defining auto transactions as well. Before I do that, I forgot to fully configure the price list table, so let's just finish that up first. I want the product ID column to be unique, so let's add a unique constraint to it and set the content alignment for better readability. I also want to enable users to specify the price on any level of the product's dimension, so I need to specify the ranked input setting and choose the product's dimension as source. Back in the Auto Transactions table, I'll add 4 columns. Product ID to identify the product that the auto transaction should be created for. Trans type identifies the type of transaction, for example, purchase cost or shipping cost. Value is the amount or percentage value of the transaction. And finally, we'll use the func column to let the user specify whether the value is a fixed amount or a percentage. You'll understand how the columns are used when we get to the calculation part of the demo. Let me just quickly add some formatting before we continue. Up until now, there's nothing special about this table. It's just a regular table with columns and some additional metadata, even though it's called auto transactions. What we want, though, is to tell the system that this table is an auto transaction table, so that it will be treated differently when used in Flow for producing auto transactions. By treated differently, we mean that Flow will provide some special APIs around the table to do search and parameter lookups in a very simple and efficient way. If you haven't heard about auto transactions before, it's our term for transactions that are created as a derivative of other transactions. For example, if you have an employee record as a base transaction, the system may produce derivative transactions, aka auto transactions, for different types of employee benefits, salary, and other aspects related to employees. To tell the system that this is an auto transaction table, I need to check the enable box here. That is all I need to do, but if I also specify the type ID column, I will not have to do any configuration in Flow later on, so let's do that as well. I actually did not have to specify the value column here. Mistake on my part. You can ignore all the properties in this screen except for the type ID column and the enable checkbox, as they are legacy and will be removed in a future version. Like we did with the price list, I'll enable ranked input on the product ID column so that users can set auto transaction rules on any level of the product hierarchy. This will make it easier for users to create rules that apply to specific products or entire categories of products. Next, I'll define a list of auto transaction types that the user can select from to specify what the value they input represents. I'll add purchase cost, shipping cost, and sales bonus percent. Then, I'll add a distribution key table for defining seasonal pricing adjustments. I'll repeat many of the steps from the auto transaction table, but this time I'll add 12 timeframe columns to represent each month of the year. This will allow for more granular control over seasonal pricing and promotions. Enabling this one to be displayed in a table explorer as well. We'll see how it looks shortly. Okay, so now it's time to add the table explorer I've been talking about and see how it works with the different tables we've created so far. I'll simply add a new page and drag drop the table explorer control onto it. This will just render an empty table explorer for now, but let's just see how it looks. To load the data into the table explorer, I'll need to go back to the designer and run its load data action. I'll do this on the page loading event, so it runs the first time the assumptions page is opened. While I'm at it, let's make a change so that the left panel slides closed when I navigate to the assumptions page, since I don't need to use the filter here, and opens when I navigate back to the main page. As you can see, I'm hooking up to the navigation events of each page and running the open and close actions of the left panel. If we now switch back to the browser, we can see that the left panel closes automatically when I navigate to the assumptions page, and the Table Explorer now lists our tables that we can click to open for browsing and editing. You might notice that the column captions in my seasonal price adjustments table does not display the actual periods, so let's quickly fix that the same way we did before, using the date start time intelligence function. While we're at it, let's also quickly fix some captions in the auto transactions table and reload to see how everything now looks. So I'm happy with how it looks, so let's go ahead and add some data. I'll add some auto transactions rules to generate purchase cost and shipping cost transactions. I'll add those to the root level so they apply to all products. Next, let's add some pricing on both product group and product item levels. And finally, we'll define some seasonal price adjustments rules for some of the products. 1 means no change, greater than 1 means a price increase, and less than 1 means a price decrease. So for example, 1.4 means a 40% increase, while 0.8 means a 20% decrease. It's time to start with the fun parts, which are the calculations. We'll do all the calculations in Flow, so let's create a flow from the designer and start building it out. What this flow will do is take the sales forecast by quantities from the user, apply a set of calculations using the price list, auto transactions, and seasonal price adjustments we just created, and then save the result back to the database so we can create a report. I'll start by adding an action to define which assumptions to use, which in our case is the price list we just created. Next, I'll do the same for the auto transactions. Before adding the seasonal price adjustments, I want to scaffold most of the flow. Before we can generate any output transactions, we need to define where it will be stored. So let's add the define calculation flow output action and select the target data store we created earlier and which columns to write to. The calculations will be done by processing one row at a time, by reading from the unpivot view we created earlier. To do this, we will add the calculation flow input action to the pipeline, where we define the data source and additional filters if needed. In this demo, we'll keep it simple and read all the rows from the data source, but in a real application, you would typically filter by dimensionality, for example, a specific department. The next thing I'll do is add a function I'll name setContext. The purpose is to tell the lookup system of the assumptions, auto transactions, and distribution keys what to use as criteria for resolving parameter values, such as the price of a product. As you'll see soon, this makes the syntax for parameter lookups very simple. How this works is that I pass in the row currently being processed from the data source. This provides the context, for example, which product, department, or account the input row is for. Then, for the lookup tables, I call the useContext method and pass in the source data row. By convention, the lookup system will use names of the columns in the source data row to match against the names of key columns in the lookup tables, so the account ID from the source will be used to match the account ID in the lookup table. The product ID from the source will match on product ID, and so on. If you do not have matching names, you can configure mappings manually here in the designer. But in our demo, we don't have to do anything because we've used matching column names in our model. I'll also call the useContext method on the output collection. This basically tells the system to automatically copy data, matching by column name, from the input row when we create a new output row, as we'll see shortly. It heavily reduces the amount of boilerplate code you have to write. You're probably wondering why all the complexity with the useContext methods? Why isn't all of this just resolved from the relationships in the model itself? The reason is that in real-world applications, the context used for lookups change multiple times during the processing of a single input row. And it happens because of custom business logic in your calculations, so the system has no way of knowing. So in real-world applications, you will usually call useContext multiple times per input row to set the context to the right values before doing lookups that depend on those context values. Your next question might be, why not just pass the context values as parameters to the lookup methods? The answer is that doing so would make the syntax for lookups more complex. You would also have to write the same code multiple times, and if you need to change which parameters to use, you would have to update every lookup instead of just calling useContext. Before implementing the calculations, I need to add the distribution key to the pipeline. I forgot to configure it properly in the InVision designer, so I'll quickly go back to fix that before proceeding. I basically just need to enable the feature and select which columns to include as factor columns. Setting the distribution key column is not really necessary when using Flow. Then, let's hook up the context to the distribution key table as well. It's time to implement our calculations. For that, I'll add another function. It will take the source row as input and use the assumptions, auto transaction, and distribution key tables to resolve parameters. I'll just quickly add the code, and then we can go through it step by step. It actually contains a bug that I'll point out, but at the same time it reveals an API for another use case, which is quite common. On line 1, we calculate the sales amount based on the quantity sold and the price per unit from our price list. So what actually happens here? We get the quantity from the input row, which is straightforward, but how do we get the correct price per unit? By simply reading the value of the price column from the price list without any form of search. This is what the calls to the useContext methods earlier enable. It lets us use a simplified syntax for resolving values in lookup tables. When you access the price property, a lookup is performed under the hoods using the context of the current row to find the matching row in the price list. This lookup is very fast and efficient, even for large datasets. For advanced scenarios, there are additional APIs you can use to perform lookups in a more traditional way. But for most scenarios, this simplified syntax is recommended. The second thing we do is find the distribution key to use, if any. The filter by context method uses the context from the input row to find the rows in the distribution table that match the context, which in our example is the product ID from the input row being processed. If there is more than one matching row, the rows are ordered by how specific the match is, in order of most specific to least specific. Because we only want the most specific match, we use the first or default method to get the first row from the ordered list of matches. First or default will return null if there are no matches, which is why we check for null in the next step. On line 5, we find the cell in the distribution key row that corresponds to the current row's period. For example, the value for January 2025 if we are currently processing January 2025 data from the source. This method gives back a tuple, which contains the date and the value of that cell. Then, on line 6, is where the bug I mentioned earlier is located. Because the input data is by month and not a total, such as a yearly total, we should use the distribution key value as is, without using the getShare API. In this case, using getShare would give us an incorrect value, as it is meant to be used when dealing with totals. I just wanted to highlight that if you are working with totals instead of monthly from the input data, you should use one of the share APIs to get the correct share value for that period. That's my story, and I'm sticking to it. Then, on line 7, we simply adjust the sales amount from the adjustment factor before we add it to the output. Adding it to the output will not immediately save to the database because that would both be very inefficient, and in many cases you want to do additional processing on the output before it's finally stored. Instead, the output is cached until we explicitly save it, which we'll do later when we're done with the walkthrough of the code. Remember from the setContext function earlier? Because we called the useContext method on the output there, the product ID and department ID from the input is automatically applied to the output as well, so we don't have to provide it explicitly. I also set the calc ID to sales amount, which will help us when building reports later. Finally, we iterate over the auto transactions to generate the shipping costs and any other auto transactions added later. Note that I should have used the filter by context method here as well, so remember to do that in your implementation. To calculate the amount per auto transaction, we use the func column to determine whether the amount is a percentage of the input or a fixed amount. And finally, we add the auto transaction to the output. Now that we're done with the calculations, let's add the final step, which is to save the output to the database. So that we don't keep adding duplicate entries for every time the flow is run, we need to add an action that deletes old records before we add the new ones that we just calculated. Then let's add the action that saves our output to the target table, run the flow, and check the results. The flow executes successfully, so let's switch back to the InVision Designer and browse the output data store. As you can see, we now have data, so what we'll do next is build a report to show both the sales forecast in amounts and the shipping costs. We'll add a SQL report that displays two series in the same chart, one for the sales amounts and one for the shipping costs. To not waste precious minutes of your life having to watch me type, I'll just paste the query. It's just a standard select with a join, where clause, and a group by. However, if you look more closely, there are some syntax here that you're probably not familiar with. The @declare_filter alias, @object_name, and @values_equal directives are InVision-specific syntax that makes the query dynamic when the report is associated with a filter in a workbook. We'll see this shortly. I also want this data set to only display the sales amounts, so I'm hard-coding a filter for that purpose as well. Let me quickly repeat the process for the shipping cost dataset. Let's switch to the Chart tab and add two series to the chart, a column series to show the sales amounts and a line series to show the shipping costs. For each series, I'll select the data source, which are the data sets I just prepared, and which columns to plot along each axis. To control how dates are rendered on the axis, I'll add a definition for the x-axis and select a preferred formatter. With the report definition done, I'll switch over to the Workbook Designer and add it to the page by dragging it in from the toolbox and sizing it to the desired size. Similar to what I did with the worksheet, I'll associate it with the department filter and make sure the report is refreshed when the filter changes. Let's preview the workbook and see how it looks. When I select departments on the group or item level in the filter, both the worksheet and report now displays the filtered data accordingly, which is just what we wanted. I now want to hook up my flow to run when I press the Save button, so that my forecast is recalculated whenever I save my changes. When the calculation is done, I also want my report to automatically refresh so I can see the effect immediately. To do this, I simply edit the tapped event of the Save button so it runs the flow after the worksheet has been saved, run the flow using the Run Flow action, and then use the Load Data action of the report to reload it after the flow has finished. Let's also update the Refresh button so we can manually refresh the report as well. Again, let's switch back to the workbook, edit and save our forecast, and see if the report updates with new data. As you can see, the report reflects the changes we made to the input. Now, let's make some changes to our parameters to check that it works as well. Let's increase the shipping cost to 10% and recalculate. Notice the values along the shipping cost series have increased. Let's increase it again just to make it very clear, then reset it back to something more sensible. The very last thing we'll do in this demo is to enable the user to write comments. We'll keep it simple by just associating the comments with the report and the department they have selected. We'll store the comments in a separate table, so let's add that first. To provide the rich text editor for editing comments, we'll use a form. Forms provide a programmatic and more flexible way of building user interfaces in InVision, but is too big of a topic to discuss in this video, so I'll only explain the basics of what we need to make commenting work. Forms provide a declarative way of building user interfaces, where you define the data, UI, and business logic in a single file. When building complex forms, you usually end up using both SQL and JavaScript to express your business logic on the back-end and front-end respectively. For this demo, however, we don't need that. The only thing we need is to point to the table where we want to store the comments and add the rich text editor control to the form. Then use the data binding syntax to bind the contents of the rich text editor to the data model so it's retrieved and saved back to the database automatically. Note that the data model expects the department ID as a parameter, so we'll pass that in when loading the form in the workbook. Now all we need to do is wire up the loading and saving of the form, just like we did with the worksheet and SQL report. When the user pressed the Save button, the changes will be saved, and when they change the selected department, the comments will be loaded. setParam value lets you pass in a value to a parameter, which in this case is the department ID we'll fetch using the Filter API to extract the selected value of the department filter. Now, for the last time, let's switch back to the workbook to test that the commenting works. And that concludes this demo. With InVision and Flow, we've built a simple sales forecast with support for calculations using financial assumptions, reporting, and commenting. Thanks for watching.